This lecture, we're going to talk a little bit about sockets and processes. And then in the next lecture, we're going to introduce this notion of a shell, which is really critical to hacking or penetrating any environment. And then we'll introduce botnets. So as we discuss sockets today, we'll introduce the idea of what is a socket. We'll talk a little bit about the TCP protocol. And then we'll look at some abstract models of how sockets work and how multiple machines communicate with sockets. So I encourage you to read the chapter, and if you prefer that to the video lectures, just go ahead and read that now. Okay, so let's pop over to the blackboard and start sketching out some of these concepts.
Okay, welcome to the blackboarding section of the lecture. One of the protocols that we looked at in our layered approach was TCP, and this stands for the Transport Layer Protocol. We need this protocol because the internet is comprised of routers, and these routers have to route millions of packets simultaneously. In the process of routing some of these packets, some packets will get lost, either due to routers becoming overwhelmed or corruption of bits and having to disregard the packet. Here we'll look at that TCP protocol and how it actually provides reliability on an unreliable network. So here's some image, right? And remember that image gets transformed into a series of bits, ones and zeros. And what happens is that these sequence of bits get broken up into packets, ones and zeros. And these packets are transmitted independently. And so one packet might get lost and the other packets might be delivered. And so in order to keep track of which packets are delivered and which packets are lost, TCP assigns a sequence number to each of these packets. So right here, this is called a sequence number. And it just lets the TCP protocol keep track of which packets. And there's a state machine inside of the TCP code that keeps track of all of these and goes ahead and says, oh, if I've lost a particular packet, now I could go ahead and retransmit. And so in order for two hosts to communicate, say we had Alice and Bob, in order for them to begin communicating, they need to exchange their sequence numbers. So Alice needs to tell Bob her starting sequence number, and Bob needs to tell Alice his starting sequence number. That way, if any packets get lost, Bob can notify Alice that he didn't receive a particular packet in the sequence, and then Alice can retransmit it. This is called the TCP Handshake. And so they're going to exchange sequence numbers so that they know what packets are outstanding. And so the first part of the handshake is called a packet or SYN packet. And this is to sync up your sequence number. So this packet says, hey Bob, my starting sequence number is 4. And then Bob will acknowledge that, send over an ACK packet, and says, okay, I've received packet 4, and now I'm expecting packet 5. The next packet in the sequence that I should see is 5. And Bob will also use this opportunity so that he doesn't have to send another message to also send his starting sequence number. So also have a SYN packet, and this might have some starting sequence number Y, and says, great, the next one I expect from you, Alice, is 5, and the next one you should expect from me is 7. 7 is my starting sequence number. And then Alice will go ahead and acknowledge that with an ACK and says, okay, I got 7, the next one I'm expecting is 8, 7 plus 1. And then once they've established their sequence numbers, now they know which packets to expect. So 7 and 6. And so now they can start exchanging data. And if anything gets lost, then they can notify the other host that they didn't receive it. And so that's the kind of basics of the TCP handshake. And you'll see these in all TCP connections. And you'll see this sometimes called SYN, SYNACK, ACK, because that's the sequence. SYN, SYNACK, and then an acknowledgement. So that's the basics of the TCP handshake. So TCP is full duplex, which means that it allows for communication in both directions. So there are three communication modes. There's simplex, half duplex, and full duplex communication. In simplex communication, it's only in one direction. So you can think of something like a telegraph. So you can only send Morse code in one direction. Half duplex is like a walkie-talkie. You can only talk in one direction at a time. So it's like, hello, over, and then the other person gets to talk and they say, hi back, over. Full duplex is like cell phone communication. So both people can talk at the same time in either direction. Because TCP is full duplex, we need a way of saying, oh, I'm ending my communication, close the communication channel. And the way we do that is with FIN and ACK packets. So here is Alice here, and she's talking to Bob. So she'll send Bob a FIN packet. She'll say, okay, I'm finished talking, but she can't close the conversation just yet. She has to wait until Bob sends an acknowledgement, say, okay, I received your FIN, that you weren't finished talking, but still she can't close this connection. Bob might still have data that he wants to send Alice. So Alice is to keep the connection open until Bob sends a FIN packet as well. Alice can start the process of closing the connection, and she sends an acknowledgement to say, okay, I acknowledge that I received your FIN packet. Once Bob receives his ACK and it has Alice's first FIN, you can close the connection. So both people have to agree. TCP connections are really useful, and they're really useful for this idea called a reverse shell. Ideally, what we want to do is we want to have some hacker machine over here, and maybe there's some victim machine in our network, and we want to be able to execute shell commands. Once we can execute shell commands, we have control of the machine. So we want to be able to have a hacker have some terminal over here, and then be able to type into this terminal and have those commands execute on the victim machine. And not only that, also get the results of those commands back to the hacker machine. And you've seen this with our first exercise where we exploited the backdoor in the FTP server, and it spawned a shell on 6200, and then you were able to communicate with the shell to control the machine and collect information. So what we want to do is we want to build our own version of that. And we'll do that in the next lecture, and here we'll discuss the concepts. So here, this is a TCP channel that gets opened. We typically refer to this channel as being associated with sockets. So just a couple of words on direction. So direction is really important here, the direction of the connection. And who initiates the connection is very important. And so let's talk about why. A lot of networks will have a firewall, and they'll also use network address translation. And so what this means is that if you have some server inside the network, it can communicate to the outside network through the firewall, and it can get to other locations like google.com, yahoo.com, because you want your employees or anybody inside your network to be able to communicate with the outside world. And so here, outgoing connections are going to be allowed. And the firewall is great because it blocks incoming connections. So if somebody was trying to get access to your network, the firewall will go ahead and block incoming connections. So incoming connections are going to be blocked. And so this is great. So if we wanted to control a machine behind a NAT, we're going to have to be a little clever about how we establish the connection. And one way we could do that is by having the shell, this thing that's going to execute our commands on the server, instead of with our previous example where we connected to it, we'll have it connect to us. So we'll have our hacker machine over here, And then instead of us trying to initiate a connection into the network, we'll have the reverse. We'll have the server reach out to us and establish a communication channel that way. And then once a channel is established, we can actually send communications into the network through that channel. And this is typically called a reverse shell, because instead of us connecting to the server is going to go ahead and connect to us. And so that's a really nice feature. So reverse shells are really useful for this reason, because they help us get around firewalls and network address translation and other things like that. So let's go ahead now and talk a little bit about how we would set up one of these reverse shells and the kind of design of it. So we're going to have two main players here in our reverse shell. The first player is our hacker machine, and then the second player is our victim machine. And so on the hacker machine, we're going to have a server, TCP server, that's going to be listening for connections from the machine. So just like a person inside the network would go out and reach out to google.com and then download the Google page. So when they reach out to google.com, they establish a TCP connection with Google, and then they will exchange data with Google. So just like that, we want to set up our server that's going to say, hey, reach out to us, and then exchange information with us. And then the victim is going to have a TCP client. And this TCP client is the one that's going to be reaching out to our hacker server to establish the connection. So let's start off by starting up the TCP server, which is normally what you start up first. So here we're going to label this the Kali operating system. And the Kali operating system is responsible for managing sockets, and sockets are going to be the means through which we communicate over the network. So the TCP server application, which we'll write in Python, same for the client, it's going to first request a socket. It says, I want to bind to some socket. And so there are a couple options. 80 is used for HTTP, and 443 is used for HTTPS. And so if you wanted to disguise your traffic as a hacker, you would say, oh, maybe I should use one of these ports so it just looks like regular web traffic. Even better is if you run your traffic over port 53, which is associated with DNS. So once you request the socket, say we requested 443, then the Kali OS is going to say, okay, I'm going to create a socket here, and it's going to have associated with it an IP address, which is going to be the Kali IP, and a port number. And that port number is going to be 443. And then the Kali OS will go back and says, okay, great, here's your socket, you can use it. And now that TCP server Python application will bind to that socket, and it will issue reads and writes. It will be able to read and write to that socket. And then anything it reads or writes from that socket will go outside through the NIC card, over the network, the internet, to whatever machine is on the other side. Okay, now let's look at the TCP client on our victim machine. So here, this is, say, running on our Metasploitable S here, which is just a version of Debian Linux. Here, we're going to do the same thing. We're going to request that a socket be created, but here we're not requesting a specific port number. We're just going to ask the operating system, Debian, the Linux operating system, to assign us one, and it goes ahead and it assigns us one. And now we have a socket that's associated with our IP address and the assigned number that the operating system has given us. It just says, here's a free port, you can use this one for your communication. Why don't we need to specify a port here? Well, things aren't connecting to the client. The client is initiating connection to something else. So in order to initiate a connection, it needs to know the IP address and port number. So the server has to have a fixed port number so that the client can know which port to connect to. But the client's going to send over its port number when it establishes the connection, so it doesn't need to specify that port number. So then here we go ahead and we'll read and write to this socket, and that will let us go ahead and reach out here to the IP address associated with our TCP server and the socket 443. So it looks like we're just communicating over HTTPS. So now that we have that model, let's look at this idea a little bit. So here's our hacker server. Here's our victim machine. And here's our clients. So we go ahead and we reach out to establish a connection. And now the hacker server can go ahead and issue commands like print working directory or reboot to the victim. And so the victim can read those commands, and then we'll have a second component here, which is going to be a Python program. And it's going to take these commands and it's going to execute them as shell commands on the operating system. And it's going to take those results and then send those results back to the hacker machine. And so now we have a way of communicating and controlling the victim machine. And so next time we'll talk about how to write this code in Python. If you're really curious, you can go ahead and read the PDF. If you're wondering, well, how do I know which ports are associated with HTTP or HTTPS or so on? Well, the Internet Engineering Task Force has a list of all of these numbers and their assignments, and they maintain them. And you can kind of read that in the PDF that is attached. So I mentioned one thing that I would talk about, which was this other really stealthy approach we're communicating on port 53. So this port's normally associated with DNS, or the Domain Name Service Protocol that we talked about last time. And so if you're in a network, some networks might have really clever ways of saying we have what's called a whitelist, which is not necessarily the most PC name, but a list of URLs that are approved. That means if your reverse shell tries to connect to an IP address that's not in this list, then it gets blocked. So an alternative approach is to go ahead and communicate over DNS. So instead of communicating directly out to one of these lists, you do a DNS query, and then the DNS server will go and search through the regular DNS hierarchy, and then it will find your DNS name server that you've written, and it will, instead of just saying, the IP address, it will also encode commands in the DNS response. And then you can control your shell. These are sometimes called implants, and we'll talk about that a little later about why, over DNS. And there's a tool called DNS2CAT that's really useful for this. And so we'll introduce this terminology of command and control, or C2, later. But DNS-based command and control is a really clever way of getting out of the network by using the DNS server as a proxy, so hiding your traffic as a DNS request. Next time, we'll talk about this idea of port scanning, how you can go ahead and use a tool called Nmap to identify open ports on a machine. And then we'll write our own reverse shell, and we'll extend this idea to botnets.
Great. So if you're enjoying these lectures, feel free to check out the full lecture series on Udemy. The link for that full lecture series is in the description below. Thanks.